Hello friends, welcome to the next lecture, lecture number 13 of Advanced Thermodynamics. In the last couple of classes, actually we were looking at equations of state for simple compressible systems. So in the first class we actually looked at the mathematical background for the relationship between various properties that are measurable and properties that are not measurable, and got an idea as to how if some properties could be measured, the other properties could be evaluated from them. At least notionally we understood that, if not in detail. And then in the last class we discussed in detail about the simplest of the forms of equation of state. So we understood that actually the equations of state need not be simple mathematical equations that relate generalized force, generalized coordinate, temperature. They could be rather complex expressions, and they could be actually different expressions in different regions of the state space. And then we said, for an example, that substances like what we called permanent gases at some point in time, like oxygen, nitrogen, hydrogen, could behave like liquids or solids or liquid vapor mixtures given the appropriate states or given the appropriate values of temperatures and pressures. And in the same fashion, something which we always believe to be solids like iron or copper could well be seen as liquids or boiling liquids or solid liquid melt mixtures and so on. So depending on the region in the state space, we can actually get things either in the solid state or in the solid liquid state or liquid state or liquid vapor state or vapor state. And given the appropriate conditions, any substance could possibly behave like an ideal gas, and any substance could possibly behave like a liquid or solid. Then we took the simplest of the equations of state, which is the ideal gas equation of state, and discussed how, if we know the relationship between PV and T, like PV by T is a constant which is equal to the universal gas constant R, where V is the molar specific volume, that is the volume occupied per mole, or we write it in the form of mass terms, then if V is the specific volume in meter cube per kg, then R is the gas constant of that substance and not quite the universal gas constant. Okay. So the relationship between the gas constant of a substance and the universal gas constant is the ratio of the two is the molecular weight. Universal gas constant divided by the molecular weight gives you the gas constant for a particular substance. So once that relationship is known, we showed how from that relationship we could derive the expressions for internal energy, enthalpy and entropy changes in a given domain. Now in this class we will spend a little bit of time exploring or understanding what happens when the ideal gas limit is not respected. What is the ideal gas limit? The ideal gas limit is when the pressure is low enough that the molecules exist as if the other molecules in the same domain did not exist. Right? So if that state is not respected, then when is that state not respected? When the pressure increases, for example, and the molecules actually come closer together, then there are two things that start happening. One is that the volume occupied by the molecules themselves is not negligible anymore as compared to the volume of the whole vessel. So there is a certain loss in specific volume because the molecules themselves occupy a significant fraction of the total volume now. So there needs to be a correction in the specific volume. Similarly, there needs to be also a correction in the pressure because the intermolecular forces start playing a role in the extent of forces that are exerted on the other molecules that are nearby. So there is a change in the pressure, and there is a change in the specific volume that is actually felt by the gas, and therefore the first set of real gas equations of state basically just did this. Okay, so one is that the volume starts becoming significant, that is the molecules which were initially assumed to be point masses with no volume of their own in comparison with the volume of the vessel, now start occupying, the volume that they are already occupying start becoming significant fraction of the volume of the whole vessel because of the pressure. And the second part is the effect of the interaction between molecules, the attractive repulsive forces between molecules on the collisions and therefore the pressure exerted on the surfaces that are there. So when these two are accounted for, then we start getting the real gas equations of state. Now there are other things also that need to be relaxed as we go on. One is, of course, the molecules were assumed to be spherical in shape. Okay. So the sphericity of the molecules start playing an important role, and not just that, the temperature, which is responsible for the molecular kinetic energy, also plays a role in the intermolecular forces. So these are the changes that keep coming in, and when we introduce these changes, then the equation of state gets more and more complex, and as the prediction by the equations of state gets closer and closer to the data, then the number of constants or parameters that need to be adjusted in the equation in order to fit the experimental data go on increasing bigger and bigger. So this is a summary of what we are going to see in real gas equations of state. So in real gas equations of state, commonly we encounter three kinds of real gas equations of state. So we'll just go to the whiteboard and start writing them. So okay, so the first form of the real gas equation of state is basically what is called the cubic equations of state. Okay, I'll explain why and what the origin of these cubic equations of state is in a moment. You already studied about this in your earlier classes. The second is the virial kind of equations of state. Okay, and the third category is the compressibility and compressibility charts. Okay, so let's start with the first one. So we said the cubic equations of state. What are these cubic equations? You must have studied about the van der Waals equations of state. So we just discussed about the pressure and volume getting altered. So the van der Waals equation of state basically says the pressure gets affected by the presence of the additional forces that are exerted between molecules, what I call the adhesive and cohesive forces. That causes an additional term called A by V squared, where V is the molecular or molar specific volume. This is the modified pressure term, And the modified specific volume is simply V bar minus B, which accounts for the volume occupied by the molecules themselves. So the pressure is replaced by P plus A by V squared, and the volume is replaced by, or specific volume is replaced by V bar minus B, is equal to the universal gas constant R into T. You compare this with P V is equal to R T for ideal gases. So the molecular distances are large when the pressures are low, and therefore the molecular distances are large. This term, because the specific volume is much larger, the A by V squared term is negligible as compared to P, and therefore this term is dropped. And similarly, the volume occupied by the individual molecules is very small, so it is neglected with respect to V bar. So you get this equation. So when those two cannot be said, then you get this. Why is this called a cubic equation of state? Because if I reorganize this equation, then I get something like this. So you just multiply throughout by V bar squared. So you get P plus A by V bar squared becomes P V bar squared plus A into V minus B is equal to RT into V bar squared, and we bring it to the left side and simplify and multiply this V bar minus B and this, so you get a V cube, and then divided by P. So the final equation looks something like V bar cube minus V bar squared multiplied by B plus RT by P okay, and plus A by P into V minus AB by P, okay, which is basically A by P multiplied by V minus B. Okay, this is equal to 0. So it gives you actually a cubic equation in V bar. So if I fix the temperature and evaluate V bar as a function of pressure, then I actually get 3 solutions for V bar at any temperature as roots of the equation, because it's a cubic equation. So this is the reason why these equations are called cubic equations of state. So this actually, if I try to plot the specific volume and temperature at various values of specific volume and pressure at various values of temperature, so I get this as okay. So this is your pressure, and this is your specific volume, and I plot it for different values of temperature. Then I get a curve that comes down like that, and it goes up and it goes down. Okay. So if I look at a certain location, there is a certain pressure range between this and this, between which there are 3 solutions that exist for this isotherm. So this is, let's say, T is equal to T1, and if I increase the temperature, then I get this going like that, and then like that, and like that. So there is this limit that moves a little closer like that, and so on. So there are this limit of this in a lower pressure, and this limit of this higher pressure. So you get this dome, inside which there is a liquid plus vapor region that remains, and this is the vapor region, and this is the liquid region, and this is the way the temperature increases, and so on. So between the saturated liquid and saturated vapor, actually we know that the stable equilibrium is a straight line like that in pure substances. So the curve of this kind actually has been found that the metastable equilibrium states actually exist between these two, and by careful experimentation these states can also be attained. So the van der Waals equation of state, or the states that are predicted by the van der Waals equation of state, are not all imaginary states, they can be obtained. So this is basically the way the equation gets plotted, and between this lower end and the higher end is a liquid vapor mixture. Below that is a liquid, and above that is a vapor. And what happens at this point where these two lines meet is the critical condition. So the pressure here is called the critical pressure, PC, and the specific volume at this location is the V bar C. Okay, and the isotherm that goes through that point actually has a saddle here, so it goes like that. So it actually goes like that, like that. So this point actually becomes a point of inflection. So there is no more three solutions, but all solutions exist at one point. So if I look at this curve and say, what is del P by del V? So this is del Y by del X at this location, and this will be 0. And similarly, because it's an inflection point, del squared P by del V squared, both will be 0 at T is equal to Tc. Okay. So using these two conditions, if I substitute into the equation that we had got here, okay. So from here, if I write P in terms of V and evaluate the derivatives and equate them to 0 and so on, and with that I can actually calculate the constants A and B because we have two equations here. So that gives me A equal to 27 by 64. So this can be derived by you. You can do the mathematics by yourself and find out. R Tc squared divided by Pc, and B is equal to RTc by 8 Pc, and we know B is equal to, or 3B is equal to Vc bar, that is the relationship that you get, or B is equal to Vc bar by 3. So if I invert these relationships and write the expression for Pc and Tc in terms of these, then I get Pc is equal to, or critical pressure is equal to A divided by 27B squared, and Tc is equal to 8A divided by 27 RB, and of course Vc is equal to, or Vc bar is equal to 3B. So okay, this is the expression that you get. So this actually tells me B is equal to Vc bar by 3 also. So this is, these two become actually equal. So if I equate these two, then I get PCVC by RTC. So it's PC VC bar divided by R into TC. Okay, so you just equate these two. So VC bar by 3 is equal to RTC by 8 PC. So this becomes actually equal to 3 by 8. Okay, so this is one finding that you have. You call this quantity PV by RT, which is supposed to be 1 at ideal gas end. This actually at the critical point you can see that it's gone much lower than 1. So this quantity PCVC by RTC is called the ZC. Z is called the compressibility factor. Okay, so this compressibility factor Z at the critical condition, that is at this location. Okay, we can calculate that to be PCVC by RTC is equal to 3 by 8, which is 0.375, right? So this is what we get from what is called the van der Waals equation of state. Okay, now This value is not quite acceptable because for most substances for which we make measurements, we find that at the critical condition, the ZC ranges between 0.23 to 0.29 by measurements. Okay, so now this expression that we have written here, it is not specific to any particular gas, but for any gas that starts deviating from ideal gas equation of state because it either approaches the saturation dome or the pressure is high for the given conditions. So if I look at this with respect to PC, you actually look at the pressure being high or low with respect to the value of P by PC and T by TC, because there are some substances for which the PC and TC values are high, for which the same value of pressure may be not so high, but for those substances for which PC and TC are low, the same value of P and T may be low, may be high. So if you look at the ratio P by PC and T by TC with respect to which you normalize, what we find is that when P by PC exceeds, let's say, 5, or when T by TC, rather when P by PC is less than 1 by 5, PC by PC, so it's P by PC is much less than 1, okay, which is in the case of this one, and P by PC and T by TC are both less than 1, then we are in the dome. In that region, because we have both liquid and vapor present simultaneously, you have a region where it is very much deviating from the ideal gas equation of state, because the cohesive adhesive forces dominate in that region. And when we go far away from this in the low pressure region, then you have the ideal gas equation of state being valid. And on this side, it's more behaving like a liquid when the pressure goes high, and T by TC is also in this region. Okay, so we basically look at P and T in terms of P by PC and T by TC. So we see that in the saturation region, near the saturation region and near the critical point, the value of Z, where actually in the ideal gas extreme the Z is 1, this goes as low as 0.375, and it goes actually in real substances, it actually goes to 0.23 to 0.29, which basically means that the ZC is substantially over predicted by the van der Waals equation of state. So the van der Waals equation of state is actually a very simple modification over the ideal gas equation of state, and it therefore doesn't seem to work in regions where the real gas behavior is quite strong. So there were multiple modifications that were made to the ideal gas equation of the real gas equation of state. So we have what is called the Redlich-Kwong equation of state, or we call as the RK equation of state, which is a variant of the equation of state that we just looked at, the equation of state of van der Waals. This is a variant of that equation, and what Redlich and Kwong did was to make the cohesion term or adhesion term, which is added to the pressure, a function of temperature as well, and he also introduced the B term inside that. So what we get there is P plus A divided by square root of T into V into V plus B. Okay, so it's not just A by V square, it's actually A by square root of T into V squared plus BV. Okay, this is the term that you have for the first one. The second term remains the way it is. P bar minus B is equal to RT. So this is your Redlich-Kwong equation of state. This actually is okay. It actually gives a value of Okay, so you fit the equations according to the measurements of PVT data and try to get the values of A and B, or you can even use the cubic conditions for the critical point and then calculate. So using that you get expressions like A is equal to 0.42748 times r squared t to the power of 2.5. So this power of half that is here actually adds this, divided by PC. This is PC. Okay, and B is equal to 0.08664 times RTC by PC. Okay, and ZC in this case, this is what we were keenly looking at. This goes to 1 by 3. Okay, so this is still 0.333, which is still substantially higher than the range of values that were obtained by measurement. So SOAF made some modification to this to get what we call the Redlich-Kwong-SOAF equation of state, where actually in this expression SOAF tried to account for the non-sphericity of the molecules, which is accounted for by using what is called the acentric factor. Okay, so in the ideal gas equation of state, we assumed that all molecules are spherical, and therefore there was a certain approximation that was involved. And somebody called Pitzer introduced this correction of acentric factor omega in order to account for the non-sphericity of the molecules. And using that omega, this equation by RK, Redlich and Kwong, was modified by SOAF. So let me write that in the next page. So you get omega. This is defined with Pitzer. This omega is nothing but minus 1 minus log to the base 10 of Psat at 0.7 Tc divided by Pc. Okay, so this is the saturation pressure at a temperature which is 70% of the critical temperature. So using that saturation data, you can actually calculate the acentric factor. So you can actually estimate the measure of non-sphericity of the molecule. So if omega is minus 1, then it is spherical, but if this number is different, then it is non-spherical. Then you define a quantity called S, which is a function of omega, which is 0.48. So this is all obtained by curve fit on the experimental data, plus 1.574 omega minus 0.176 omega squared. And using this S, you define an alpha, which is equal to 1 plus S times 1 minus square root of T by Tc, the whole square, okay, at any given temperature. So alpha is a function of temperature. Okay, so the expression square root of T at in the denominator was replaced with an alpha in the numerator. So RKS equation of state looks like P plus A alpha divided by V into V by V plus B multiplied by V minus B. This term remains the same, is equal to RT. But with this sophistication, the ZC did not change. This remained at 0.333, that is 1 by 3. So then came the other form of cubic equation of state, which is due to Peng and Robinson. So the Peng-Robinson equation of state makes this equation a little bit more cumbersome. So it makes it P plus it is A alpha divided by V into V plus B, as it is there already. And in addition, there is one more term here, plus B into V minus B. Okay, so the equation for the interactive forces or the cohesive adhesive forces gets more and more complicated with this. This multiplied by this part fortunately remains the same. V minus B is equal to RT, and this gives a ZC value of 0.307. And what was found is that with cubic equations of state you are not able to get anything better than this, but this is much closer than the 0.375 of van der Waals equation of state, or for that matter 0.333 of Redlich-Kwong or Redlich-Kwong-Schwab equation of state. Okay, so these are the best that you can get, and with this, of course, these equations are still with a reasonable simplicity. You can actually use these to obtain the relationship between PVT, and therefore if you want to get the other properties which require the derivatives of these quantities, pressure with respect to temperature or volume with respect to temperature, you can still evaluate them using these algebraic expressions and eventually get the changes in specific heat and changes in internal energy, enthalpy and entropy, with of course some calorimetric measurements of specific heats. Okay, so this is what about the cubic equations of state. We'll stop here for this class. In the next class, we'll try to look at the other forms of real gas equations of state, which is the virial equation of state and the compressibility charts. Okay, so we'll stop at this point.